All right, welcome to Miss Thomas's floor teaching. So I had a question about galvanic cells and reduction oxidation and how that works. So I'm going to try and do that as best as possible from my living room floor. So you guys should already know that oxidation is a loss of electrons. So in this particular case, for example, tin here, this is an oxidation reaction because it's losing electrons. The electrons are on the right-hand side. The reduction half equation in this particular case is this one because the electrons are being gained. They're a reduction, so the electrons are a reactant. So this is our reduction half equation here. We can put those together because I've got 2 electrons on this side and 2 electrons on this side. I can cancel them out. And I get this as my overall half equation. You guys obviously will need to include states, but that's how your oxidation reduction works. Now, when we're looking at our E naught value table, and I've put a few of those values up here just to kind of mess with for the minute, you will have them all listed as reduction half equations. Your hydrogen, or your standard hydrogen electrode, is this one here. You've got hydrogen ions reacting with electrons to give us a hydrogen gas molecule. This is the standard reference for all of the other reduction half equations on that table, and they've set that at 0 so that we can then compare those other values to it, because they needed to have some form of reference to begin with. So this one up here, this is your strongest reduction equation going on here because it has the highest electrode potential, right? Down here at the bottom, lithium 2 plus ion is not going to be reduced. It's going to be the least likely to be reduced, right? Because to gain those 2 electrons to form lithium solid is going to take energy in, right? That's a minus there. So to do this particular reaction, it needs to gain a fair amount of energy for that to happen. So when we're looking at whether or not a reaction will spontaneously occur or not, I always say, like reading a book, we start from the left, and if we're going down the hill, then we're going to have a spontaneous reaction. So the example of this that I have is if I start with fluorine gas and I start with tin metal, right, in a cell, because I'm going down the hill, right, that will happen spontaneously. And I can look at that by doing a calculation of the electrode potential. So the electrode potential of that particular galvanic cell will be the reduction minus the oxidation. You do not change the signs or the numbers of this, even though you are flipping that particular equation around to make it the oxidation equation, and you have the tin going backwards to be the tin 2 plus ion. Leave it as is. So reduction minus oxidation is going to be 2.87 positive number minus negative 0.14, right? The 2 negatives become a positive here. So when I add that up, I find that 3.01 volts will be the potential, or the potential difference given out by that particular galvanic cell, right? If I have to do something different and I'm going the other direction, if I'm going up the hill, right, if I start from the left and I've got iron 2 plus and I have to go up to say copper, this is not a spontaneous reaction because, like going up a hill, it takes energy to do that. If I'm going down a hill on a bicycle, I can just sit there and do whatever, no problem. If I have to go up the hill on a bicycle, I've got to make a whole lot of effort, pedaling, energy in. It's going to be a pain in the butt, right? So when I am going up the hill, that tells me that I am going to have a non-spontaneous reaction. So if I do that, I've got iron 2 plus 2 electrons goes to iron solid. And I've got the copper solid going back to become the copper 2 plus iron and the 2 electrons over here. I can do my overall equation because I've got 2 electrons and 2 electrons here. They can cancel each other out. When I do my electropotential equation here, I have the E naught value as the reduction minus the oxidation again, except my reduction is negative 0.44. I have this here, and I am taking away a positive 0.34. I find out at the end of that I have a negative value. That negative value tells me that I need to put at least that many volts in to get that particular reaction to work. If I don't, it's not going to happen. Typically, when I have spontaneous reactions, those things are used in galvanic cells. They're used to create batteries. But when I have something going up the hill that's not spontaneous, that's going to require electrolysis. I'm going to need to put an electric current into that particular reaction to get that to happen. Any other questions about that? Let me know. Otherwise, peace out from living room floor chemistry.